The megathrust earthquake itself lasted only 5 to 7 minutes, but the danger stretched on for 3 centuries, starting the moment the ocean floor locked against the continental crust in the winter of 1700. And that first violent slip was just the opening scene of a geological cycle that never truly ends. Over the following decades, scientists watched the coastlines of the Pacific Northwest slowly rebound, the land inching upward as tectonic pressure rebuilt itself in the dark. By the time we are done here, you will understand exactly what ocean-bottom seismometers may have captured just off the coast of Oregon, and why a recent anomaly could change our timeline for the next great American disaster. Today, we are going to break down exactly what is going on, where it is most dangerous, and whether things could get even worse. No guessing, no dramatizing, just the facts, the science, and the real stakes. Drop a comment right now. Have you ever personally felt the ground shake in the Pacific Northwest, or lived through a major seismic event anywhere in the world? Tell me where you were and what it felt like. If you want to be the first to know every time something major happens, subscribe. It is completely free. A thumbs up also helps enormously. Let us go for 5,000 likes on this one, so the algorithm actually shows it to people who need to see it. Now, let us get into it. On a quiet Tuesday morning in late June 2026, a fleet of ocean-bottom seismometers anchored 40 miles off the coast of Newport, Oregon, began transmitting an unusual sequence of data packets to the Pacific Northwest Seismic Network. At 4:17 a.m. Pacific time, the sensors picked up a low-frequency pressure pulse sitting below the range of human hearing. This was not a standard tectonic rupture. It was an infrasound signature of deep Earth movement, registering a steady, rhythmic vibration that lasted for 72 consecutive hours. To put this in context, standard earthquakes release their energy in seconds. This event was stretching across days. The instruments, part of the Cascadia Initiative Array, recorded hundreds of microtremors, none exceeding a magnitude 2.8 on the Richter scale, yet occurring in a tightly clustered zone 25 miles beneath the seafloor. If you follow seismic news at all, that specific depth probably already rings a bell. It sits exactly on the interface where the Juan de Fuca plate is diving beneath the North American plate. But here's the part nobody expected. While the surface remained completely still, GPS stations along the Washington and Oregon coastlines detected a sudden, millimeter-scale shift. The land was moving westward, toward the ocean, by exactly 4 millimeters over a 2-week period. That changed fast. In the world of geophysics, 4 millimeters of sudden crustal deformation is the equivalent of a siren. Scientists generally do not conclude that a megaquake is imminent from a single slow-slip event, but the sheer volume of energy released deep underground forced a quiet reassessment of the fault's current stress profile. To understand why a few millimeters of movement sent shockwaves through the geological community, we have to rewind to the winter of 1700. For decades, the Pacific Northwest was considered a seismically quiet zone. Geologists in the 1960s and 70s looked at the Cascadia Subduction Zone and saw a smooth, benign trench. They believed the plates were gliding past one another smoothly, without locking. But that assumption was shattered by a completely different kind of evidence. In the late 1980s, geologist Brian Atwater began investigating the coastal estuaries of Washington state. He found something terrifying: vast ghost forests. These were stands of massive Sitka spruce and western red cedar, their trunks still rooted in the soil, but entirely dead. Tree ring dating revealed that all of these trees died in the exact same year, and more specifically, they died between the summer of 1699 and the spring of 1700. The trees had not died from disease or fire. They had drowned in salt water. The land they grew on had suddenly dropped by up to 6 feet, instantly submerging the root systems beneath the tidal zone. But the most damning piece of evidence came from an ocean away. In Japan, historical archives from the Edo period documented a massive, orphan tsunami that struck the coast of Honshu in January 1700. There was no local earthquake recorded before the waves hit. Japanese historians and American geologists collaborated, running computer simulations of tsunami wave propagation across the Pacific. The only mathematical model that perfectly matched the Japanese wave heights and arrival times was a magnitude 9.0 megathrust earthquake originating off the coast of North America, rupturing a fault line over 600 miles long. The Cascadia Subduction Zone was not quiet. It was a sleeping giant, and it had woken up with apocalyptic force just 3 centuries ago. Since that discovery, the narrative of the Pacific Northwest has been defined by a single, looming question: when will it happen again? The geological record shows that Cascadia has ruptured in magnitude 9.0 events roughly every 500 years, though the intervals can range from 200 to 800 years. We are currently at year 326. The strain is accumulating right now at a rate of about 40 millimeters per year. That is roughly 1.5 inches of tectonic pressure building up every single year, locked in place by friction along the megathrust fault. Over 3 centuries, that equates to over 40 feet of stored elastic energy, just waiting for the rock to fail. And that stored energy is what makes the recent warning signs so critical. The slow slip event detected in June 2026 is known as episodic tremor and slip, or ETS. It happens roughly every 14 months in the deeper, hotter sections of the fault, where the rock is ductile enough to glide slowly rather than snap violently. Normally, ETS relieves a small amount of stress, but the recent data showed an anomaly. The tremor duration was 30% longer than the historical average, and the GPS slip vector was shifted. Instead of releasing pressure evenly, the deep fault appeared to be transferring stress upward toward the shallower, colder, and more brittle section of the subduction zone. This is the locked zone. This is the section that will eventually snap. To put a magnitude 9.0 earthquake in context, we have to look at the sheer physics of a subduction zone. The Earth's crust is not a single, solid shell. It is broken into tectonic plates that float on the semi-fluid mantle beneath. Off the coast of the Pacific Northwest, the oceanic Juan de Fuca plate is being forced eastward, diving beneath the continental North American plate. This process is called subduction. As the dense oceanic crust sinks, it drags the edge of the continental crust down with it. Imagine bending a thick wooden ruler. You apply pressure, and the ruler bows downward, storing immense elastic energy. The rock of the North American plate is currently being bent downward, compressed, and warped by the relentless push of the Juan de Fuca plate. The friction between the two plates is so intense that they become completely locked together. The continental crust acts like a giant spring, coiled and under extreme tension. When the stress finally exceeds the frictional strength of the rocks, the fault ruptures. The bent continental crust violently snaps back to its original, unbent shape. This process is called elastic rebound. When the Cascadia fault ruptures, the seafloor will instantly thrust upward by as much as 60 feet. This sudden vertical displacement of the ocean floor is what generates a tsunami. But the energy release does not stop there. The rupture will propagate southward from Vancouver Island down to Cape Mendocino in Northern California, traveling at roughly 2.5 miles per second. The shaking will not be a brief jolt. It will be a sustained, violent rolling motion lasting anywhere from 4 to 7 minutes. In a standard magnitude 7.0 earthquake, the intense shaking might last 10 to 15 seconds. In a magnitude 9.0, the duration is what destroys modern infrastructure. Buildings are engineered to withstand sharp, short shocks. They are not engineered to endure 5 continuous minutes of high-frequency lateral acceleration combined with low-frequency rolling waves of ground displacement. The soil itself will lose its cohesion. Liquefaction will turn solid ground into a thick, churning soup, causing bridges to collapse, underground fuel tanks to float to the surface, and entire neighborhoods to sink into the mud. But here is the problem with the physics of the Cascadia Subduction Zone. The danger is not limited to the shaking. The vertical uplift of the seafloor displaces billions of tons of water, creating a series of massive waves that radiate outward. For the coastal communities of Oregon and Washington, the tsunami is the ultimate clock. The moment the shaking stops, the countdown begins. In towns like Seaside, Oregon, or Westport, Washington, the first wave will arrive in as little as 15 to 20 minutes. There will be no time to wait for official sirens or emergency broadcasts. The earthquake itself is the only warning. The water will initially recede, exposing hundreds of yards of bare seafloor, a phenomenon that historically draws curious onlookers to their deaths. Then, the ocean returns. These are not surfing waves. They are massive walls of churning debris, moving at 30 miles per hour, carrying cars, houses, and shipping containers like toys. The inundation zones mapped by the National Oceanic and Atmospheric Administration show that water will surge miles inland, following river valleys and low-lying coastal plains, completely wiping out the primary evacuation routes. And yet, the mechanism of destruction extends far beyond the coast. The seismic waves from a magnitude 9.0 event will travel through the bedrock of the continent, reaching cities like Seattle, Portland, and even Eugene with enough force to cause severe damage. But the geology of the Pacific Northwest amplifies the threat in specific, devastating ways. Seattle is built on a complex web of fault lines and sits atop the Seattle Basin, a deep sedimentary bowl that traps and amplifies seismic waves. When the shaking hits, the basin will act like a bell, ringing and extending the duration of the violent motion. Portland, situated further inland, faces a different threat. The city is laced with unreinforced masonry buildings. Structures built before the 1970s, constructed from brick and mortar without steel rebar. These buildings are incredibly vulnerable to the lateral forces of a long-duration earthquake. The mechanism of failure is simple and catastrophic. The mortar cracks, the walls bow outward, and the heavy brick facades collapse directly onto the sidewalks and streets below. These are not just geological events. They are human experiences. To understand the sheer scale of the human stakes, we have to look at a stark contrast. The difference between Japan's 2011 Tohoku earthquake and the projected Cascadia event. On March 11, 2011, a magnitude 9.0 earthquake struck off the coast of Japan. The shaking was violent, but Japan had spent decades and billions of dollars preparing for this exact scenario. Their early warning systems detected the primary seismic waves and automatically shut down high-speed bullet trains, halted manufacturing assembly lines, and sent alerts to millions of cell phones seconds before the worst shaking hit. Their coastal defenses included massive seawalls, some reaching 40 feet high, and rigorous, mandatory evacuation drills that were ingrained in the culture from childhood. Even with that unprecedented level of preparation, the resulting tsunami overwhelmed the defenses, leading to nearly 20,000 deaths and the Fukushima Daiichi nuclear disaster. The difference between Japan and the Pacific Northwest is not luck. It is investment and preparation. And right now, the Pacific Northwest is vastly underprepared. Consider the coastal towns of Oregon. Many of these communities are built entirely within the tsunami inundation zone. The primary arteries of evacuation, such as Highway 101, are heavily dependent on a series of aging bridges that cross narrow river estuaries. In a magnitude 9.0 event, geotechnical engineers project that a significant percentage of these bridges will suffer critical structural failure or be blocked by liquefaction and landslides before the tsunami even arrives. The residents will be trapped on the wrong side of the water. In contrast, look at the preparedness initiatives that are currently fighting for funding. In Westport, Washington, the community recently completed the first vertical evacuation structure in North America. It is an elevated steel and concrete platform built directly onto the roof of an elementary school, designed to hold over 1,000 people safely above the tsunami wave height. It is a marvel of engineering, but it is just one structure, protecting one small fraction of the vulnerable population. The rest of the coast relies on foot races up steep, heavily forested hillsides, in the dark, amidst the chaos of collapsed infrastructure and panicked crowds. The human stakes extend deep into the urban centers as well. Portland and Seattle are home to millions of people, dense networks of critical infrastructure, and vital economic hubs. A prolonged outage of the regional power grid, combined with the severing of major fiber optic communication lines, would plunge the region into darkness and isolation. The water treatment facilities, many of which rely on electric pumps and aging pipes running through unstable soil, would fail. The delivery of medical supplies, food, and clean water would grind to a halt. The contrast is glaring. We live in an era of unprecedented technological advancement, yet our foundational infrastructure in the Pacific Northwest was largely built before the true nature of the Cascadia Subduction Zone was even understood. We built our cities on a ticking clock, assuming the fault was dead, and now we are racing against time to retrofit a century of urban development. The fear lives in the facts. The fact is that millions of people are currently living, working, and sleeping in structures that cannot withstand the sustained violence of a full margin rupture. But here is the part that keeps emergency managers awake at night. It is not just the immediate casualties of the shaking and the wave, it is the cascading failures of the aftermath. The Pacific Northwest is heavily dependent on a few critical transportation corridors. Interstate 5, the main artery connecting Washington, Oregon, and California, crosses dozens of overpasses and bridges that were not designed for long-duration seismic loading. If I-5 is severed at multiple points, the region is effectively cut off from the rest of the country. The ports of Seattle and Tacoma, which handle a massive percentage of the nation's maritime trade, would be crippled by damaged cranes, liquefied docks, and sunken vessels. The economic impact would ripple across the globe within hours. And in the isolated coastal communities, the lack of heavy machinery to clear debris means that search and rescue operations could take days, if not weeks, to reach the hardest hit zones. The human experience of the Cascadia event will be defined not just by the terrifying minutes of the earthquake, but by the grueling, isolated months of survival that follow. So, what are scientists watching next? The recent slow slip event and the anomalous GPS data are just pieces of a much larger puzzle. Geophysicists are currently deploying a new generation of offshore monitoring equipment to get a clearer picture of the fault's behavior. The Ocean Observatory's initiative's cabled array is a network of sensors laid directly across the seafloor, providing real-time, high-definition data on fluid pressure, temperature, and microseismicity. By monitoring the exact locations where the deep fault is slipping, scientists hope to identify the specific stress transfer mechanisms that might trigger a rupture in the shallow, locked zone. They are looking for the precursors, the subtle changes in the Earth's crust that might provide a few hours or days of warning before the main event. But the hard truth is that scientists cannot accurately predict the exact time, date, or location of an earthquake. The physics of rock failure deep underground are too complex, and the variables too numerous. The warning signs we are seeing now are indicators of a system under immense active stress, not a countdown clock to a specific day. Keep an eye on the strain accumulation rates, too. Recent studies utilizing advanced LIDAR mapping and high-precision GPS networks have revealed that the locking depth of the Cascadia Fault varies significantly along its length. Off the coast of Washington, the fault is locked all the way to the surface, meaning the entire margin could rupture in a single, massive magnitude 9.2 event. Further south, off the coast of Oregon, the locking zone is shallower, and the fault might rupture in a series of smaller, though still devastating, magnitude 8.0 events. This segmentation is critical for understanding future risk. A full margin rupture is the worst-case scenario, unleashing the maximum possible tsunami and shaking across the entire region. A partial rupture would spare some areas the worst of the shaking, but could still generate localized, highly destructive tsunamis that strike with terrifying speed. The regions most exposed to the immediate tsunami threat remain the low-lying coastal plains, the estuaries, and the river valleys that funnel the water inland. Cities like Crescent City, California, have a long, tragic history of tsunami damage from distant earthquakes, and their unique harbor geometry acts as a funnel, amplifying incoming waves. What would have to happen for the worst-case scenario to unfold? The entire 600-mile length of the megathrust fault would have to fail simultaneously. The rupture would initiate at a single asperity, a point of extreme friction and stress, likely deep beneath the Olympic Peninsula or off the coast of northern Oregon. From there, the tear would propagate outward, unzipping the fault line at supersonic speeds. The energy released would be equivalent to detonating tens of thousands of megatons of TNT. The continental crust would snap back, lifting the coastline by several feet and instantly altering the maps of the Pacific Northwest. The resulting tsunami would not only devastate the American coast, but would cross the Pacific Ocean, striking Hawaii, Japan, and the Philippines with destructive force hours later. This is the reality of living on the Ring of Fire. The tectonic forces that build our mountains and shape our continents are the exact same forces that can erase our cities in a matter of minutes. The dread is not irrational. It is a direct consequence of the ground we stand on. Despite dramatic online headlines and the terrifying implications of the recent offshore data, there is currently no scientific evidence that the Cascadia Subduction Zone is going to rupture today, tomorrow, or even within the next decade. The Earth operates on geological timescales, not human news cycles. The slow slip events and the microtremors are natural, expected behaviors of a complex subduction system. The supervolcano of seismic energy is not waking up this afternoon. The most realistic danger isn't buried miles underground at all. It is hiding quietly just a few feet beneath the ground people are standing on right now. It is the unreinforced masonry building you walk past on your way to work. It is the aging bridge you drive over every morning. It is the lack of a week-long emergency kit sitting in your hallway closet. The real threat is our complacency in the face of a known, inevitable geological reality. We have the science. We have the maps. We know exactly where the water will go and which buildings will fail. The only variable left is human action. Retrofitting structures, reinforcing infrastructure, and establishing clear, practiced evacuation plans are the only ways to mitigate the inevitable. The fear generated by the sheer scale of a magnitude 9.0 event must be converted into practical, localized preparedness. If you live in the Pacific Northwest, know your tsunami zones. Know the structural integrity of your home. Have a plan for when the cell towers go down and the roads are blocked. Drop a comment right now and tell me if your city has a clear vertical evacuation plan or if you are still relying on luck. Let us go for 5,000 likes on this one so the algorithm actually shows it to people who need to see it, and let us separate the geological facts from the sensational noise. The ground beneath us is alive, and it is keeping a record of every inch of pressure we ignore. Let us go. See you in the next one.